Hi, have you ever wondered why two counties growing the exact same crop in the same season can produce dramatically different yields? In the United States Corn Belt, that gap is a massive difference that directly impacts food supply, pricing, and agriculture sustainability. So, what's really driving that variation? Is it farming practices or something deeper, like climate? In this project, I built Corn Belt Performance Analytics, which is a fully containerized end-to-end data platform designed to answer that exactly. By combining agriculture data with climate records, this system analyzes how environmental factors influence crop performance at a granular level. From data ingestion to pre-processing and automated pipelines with Apache Airflow to interactive dashboards with Superset and even a conversational agent that translates natural language into SQL, this project brings together a full modern data stack. In the next few minutes, I'll walk you through the architecture behind the system, the data engineering pipeline, and the key insights we uncovered about climate and yield variability. So let's dive in. Before we get into the system, let's talk about why this project exists in the first place. Three numbers, that's all it takes. 33%, one third of all the corn produced on the entire planet comes from the United States. When American harvests struggle, global food prices feel it. That's the scale we're talking about. 15.2 billion bushels harvested in a single year, 2023. To put that in perspective, that's enough corn to fill over 1 million Olympic swimming pools. The American Corn Belt is not just a farming region, it is one of the most critical agriculture systems on Earth. And then 84 bushels per acre. This one is the most interesting number among the three, because this is the gap, the performance gap between the best producing state and the worst producing state, in the same region, the same year, under broadly the same conditions. And that gap is the entire reason this project exists. Because if two counties are farming the same crop in the same belt in the same year, and one is producing dramatically more than the other, something is explaining that difference: weather, soil, temperature, rainfall. The question here is, can we measure it? Can we quantify it? Can we build a system that actually tells us why? I've been mentioning the Corn Belt from earlier. Well, you see that orange region on the map? That's it. Right in the heart of the United States. It stretches across the Midwest and holds some of the most fertile land on Earth, with a climate that, in the best years, is almost perfectly suited for growing corn. Surrounding them, there is Nebraska, Kansas, Missouri, Indiana, Ohio, and Minnesota. Hundreds of counties, each with its own climate, soil, and conditions. We've got 8 states, hundreds of counties, and 10 years of data. And just one question: why do some of these counties consistently outperform the others? Starting with the datasets we used. Usually, when working with the US agriculture and climate data, two major sources often come up: USDA and NOAA. USDA datasets come from the United States Department of Agriculture. They mainly focus on agriculture and farming, things like crop production, yields, soil conditions, farm economics, and food supply. On the other hand, NOAA datasets are all about weather, climate, and environmental conditions. They include data like temperature, rainfall, drought, storms, and long-term climate trends. And since we wanted to combine both, we could uncover powerful insights about how climate directly influences agriculture productivity. Let's walk through the architecture behind the system. At the bottom layer, as I said, we start with data sources, NOAA and USDA. NOAA data is fetched automatically through bash scripts using an API, while USDA data comes in structured CSV files. This data is then ingested into PostgreSQL, which acts as the central analytical database. Inside PostgreSQL, we store 4 core tables, and on top of them, we built 3 analytical views. Now, what makes this pipeline fully autonomous is Apache Airflow. Airflow schedules, monitors, and manages every step, from data ingestion to database updates. No manual intervention, just a fully automated workflow running on a defined schedule. On the visualization side, we have Apache Superset. It connects directly to PostgreSQL through Docker's internal network, meaning the dashboards are always live. As soon as the data updates, the visuals updates instantly. And finally, at the top layer, there is an AI assistant This allows users to query the system in plain English or French and get structured answers. No SQL required. So in this architecture, each block you see plays a role. Data sources, database, then orchestration, visualization, and intelligence. 5 components, 1 containerized environment, transforming raw data into real-time actionable insights. In that original question, well, now we do have a system powerful enough to answer it. Let's break down the backbone of our system, the database. We have 4 core tables, all connected through geography, the counties. And each county has a unique FIPS code. That code ties everything together, yields, weather, even the stations measuring the climate. The first table is the yields table. It stores harvested area, corn yield, market price, and total production value for each county each year. This is where performance lives, the difference between a county producing 210 bushels per acre and one with 126, for example. Every chart, ranking, and KPI comes from this table. The second one is the monthly weather table. Here, weather is stored month by month, not just yearly averages. You might ask why? Well, because corn is so sensitive to very specific periods, just like June to August. Heat waves, droughts, heavy rainfall during the growing season all show up here, making the link between weather and yield meaningful. The third table, weather stations. It tracks all stations across the Corn Belt, which countries they cover and which year they're active. It ensures data quality and completeness. You can tell if a county's weather record is reliable or needs attention just based on this table. And the fourth table, the last one, is the counties one. This is the ANCO, the reference for all other tables. Every yield, every weather observation, every station points back here. Now, row tables are great for storing data, but they do not give you answers. That's where analytical views come in. Think of a view as a pre-built question. Instead of recalculating complex queries every single time, the database does it once and you can use it instantly. The first view we use is the county performance one. It aggregates yield, price, and revenue for each county across all years. This powers rankings and KPIs. Every chart showing which counties are outperforming comes from here. The second view is the seasonal weather. It transforms raw monthly weather into agronomic indicators. Summer temperatures, rainfall totals, heat stress, water stress, etc. This database doesn't just store weather, it interprets it. The third one is the state-level KPIs. This is the executive summary. Key metrics consolidated by state with national rankings and calculated automatically. It feeds the live dashboard in Apache Superset. And now let's jump into the demo and watch the system turn data into real-time insights. It all starts here. One terminal command, Docker compose up, and 11 containers spin up simultaneously. The database, the ETL pipeline, Airflow, Superset, a Redis cache, a seeder, the chatbot. Everything live in under 2 minutes. No manual setup, no configuration headaches. Now let's move on to the AI chatbot. This is where the system becomes truly accessible. Open the assistant interface and you type a question in plain English and the system handles everything. For example, let's ask, show me the yield evolution since 2015 by state. The assistant instantly generates a structured analysis. It highlights trends, identifies top and bottom performance states. It even renders a live interactive charts directly in the conversation, even though it's taken quite a long time to appear. The left sidebar gives quick access questions, yield evolution, state comparisons, top counties, precipitation impact, price correlations, one click, and answers appear instantly. This is not a generic chatbot, it's a domain-specific analytical assistant connected live to the agriculture database I introduced earlier. Let's zoom in on a specific state over several years. The response is immediate and precise, showing evolution over time, peak performance, and actionable recommendations for a comparison with neighboring regions. Moving to country-level insights. First, the state yield comparison chart. A bar chart ranking all states by corn yield. Performance disparities are instantly visible here. Behind the chart, there is the KPI table that tells the economic story. The dashboard shows yield, revenue, land exploitation, putting performance gaps in clear context. Then the yield gap by state. This chart shows which states are above or below the national average. This visualization quantifies opportunities for improvement at a glance. Now on to the Apache Superset, or the visualization layer. The summer temperature gauge and hydric stress distribution charts provide actionable environmental indicators, heat stress, irrigation priorities, and overall resource allocation. And once we log into Airflow, the interface gives us a clear overview of the entire pipeline. At a glance, we can see all the DAGs that run daily: data quality, ETL pipeline, KPI ETL, KPI refresh, and superset refresh. For each DAG, the interface shows its current status, whether it runs successfully, failed, or is still in progress, along with execution times and historical runs. You can also click into each DAG to see detailed logs, task dependencies, and the sequence of steps, which make it easy to track, troubleshoot, and ensure that every part of the workflow is running smoothly and automatically. That's it. That's Corn Belt Intelligence in action. From automated data ingestion, cleaning, transformation, to live dashboards and AI-powered analytical assistant, the system turns raw agriculture data into actionable insights, all fully automated, fully connected, and accessible to anyone, technical or not.